Section 1.1, also part of section 1.2. We'll be talking about system of linear equation, and we'll be expressing these equations in terms of a concept called matrices. The linear equation looks like this: a1x1 plus a2x2 all the way a(n)xn plus b. Notice we avoid using what? Alphabets, because alphabets, there are 26 letters in the alphabets, English alphabets. So if the number of variables exceeds 26, then you'll be running out of letters. So therefore, we would denote the variables with subscript like x1, x2, x4, x5, and so on and so forth. System of linear equation, they come in a variety of forms. System of linear equation means what? You have multiple linear equations considered to be at the same time. Okay? So system of linear equation can be what? 2 equations, 2 unknowns, 3 equations, 3 unknowns, 2 equations but 3 unknowns, 2 what? 3 equations but only 2 unknowns. In other words, in these cases, the number of equations matches the number of variables, whereas here you have less equation than the variables. Here you have more equations than the variables. So we would like to examine the solution of these kind of system of linear equation in this section and upcoming sections. So to begin with, we need to introduce a concept of matrix. Those of you who have the matrices, experience with matrices, so this should be pretty much right up your alley. So matrix in general is a rectangular array of quantities like numbers, and usually it's shown either by set of parentheses or brackets, and we denote the letter name of the matrices by capital letters. For instance, this is a matrix which its elements or members of this matrix is 3, -1, 0, 5. The dimension of a matrix is denoted by the number of rows and columns. The first number right here is always what? The number of rows, correct? So this would be number of rows. And the second number always will be what? Number of columns. Do you see it? So this guy is called 2 by 2 matrix because the number of rows matches the number of columns, so we call this a square matrix. However, this guy has only 3 rows but 1 column, so the dimension is 3 by 1, and those matrices which either they have 1 column or 1 row, they are considered to be a vector. In other words, we call this 3 by 1 vector a column vector, because this corresponds to a point in space. Do you see it? On the other hand, this matrix C has 2 rows but 3 columns, so it's 2 by 3, so that's the dimension of the matrix, which is denoted right below the matrix. As I said, if you have either 1 column or 1 row, these guys are considered to be vectors. So if you have 1 row and 3 columns, so that's 1 by 3, and that's called row vector. In general, you can denote the elements of a matrix by lowercase I subscript ij. I is the what? Number of rows. J is the number of columns. For instance, if I want to express this in general format without telling you what the elements are, I would say, hey, I have a 2 by 2 matrix which it has 2 rows and 2 columns, and the elements of that matrix happens to be aij. In other words, this guy is called a11, this guy is called a12, this is 21, and that's 22. What does that mean? That means this is the element in the first row, first column, first row, second column, second row, first column, second row, second column. So that's what those subscript are, and usually is denoted by ij. So that's basically matrix notation. So now we have something called elementary row operations. Remember, when you solve these kind of equations in algebra classes, you were able to what? Either switch the what? Equations, or multiply an equation by a non-zero scalar, or add a multiple of one equation to the other equation. Remember, that was called elimination or addition method. Well, turns out those operations, which are known as elementary row operation, and the acronym is ERO, still holds true for matrices. In other words, if you have, let's say, a system of linear equation like so, usually the system is written as AX plus B, where A is a matrix of coefficients, X is the matrix of variables, and B is the constants on the right side. So in this particular case, A is the coefficient of variables. Notice it's 1, -2, -1, 3. There it is. So matrix of coefficients is a square matrix, which is 2 by 2. Does it have to be square? Not really. X, the vector X here, is this column vector, which is x1, x2. Those are your unknowns. And the constants on the right side is denoted usually by B vector. Remember, that's a vector as well. So is this guy, because these are column matrices, column vectors, which happens to have so many rows, one what? Column. So those are like column vectors. So this is a matrix of variables. This is a matrix of columns. So row vector is any vector with what? One row and many what? Columns, such as this guy is a row vector. Column vector is n many rows but one column, such as this guy, which is like 4 by 1, whereas this guy is 1 by 3. The general form of the matrix, so as I said, the elements of the matrix are denoted by A11, A212, A13, all the way to A1n. And let's say you have m many rows and n many columns, so the last one would be AMN. So the way we write this, instead of listing all these elements, we just say, hey, we have a matrix whose elements happens to be lowercase aij. I goes from 1 to m and j goes from 1 to n. Remember, I represents the rows, j represents the column. This kind of format is usually used when you're proving what? Theorems in matrix field. Then we have something called augmented matrix, which is denoted by A with, like, think of it as a hashtag kind of a deal, symbol. So the augmented matrix for a system of linear equation in any dimension is first you what? List the coefficient of the variables on one side of the vertical line and the constants on the other side. So in this system, the coefficients are 1, -2, -1, 3, a line separating coefficients from constants on the right side, -1, 3. This matrix, which is what? 2 by 3, is called an augmented matrix. So we augmented what? The constants to the matrix of variables. So in this case, you got x1 minus 2x2, x3 equals 0. 2x2 minus x8, x3 equals 8. 5x1 minus 5x3 is equal to 10. Augmented matrix is 1, -2, 1, 0. 0 because there is no x1. 2, -8, 8. Here there is no x2, so there is a 0 for x2, but that x1 is coefficient of x1 is 5, coefficient of x3 is -5, and the constant is 10. So this guy is 3 by 4 matrix, and it's called augmented matrix. Diagonal elements is only relevant when you're talking about square matrices. Diagonal elements happens to be these guys. These are called diagonal elements. Anything else is called off-diagonal elements. So the only diagonal elements in this is square matrix. Notice you gotta have a square matrix to find the diagonal elements, which in this case is 3, 7, and -4. Next item is called trace, or excuse me, transpose of a matrix, denoted by this. The transpose of a matrix, remember this is 3 by 2. 3 rows and 2 columns, you just reverse the columns and rows. So in this case, it will be what? 2, 3, 9, 5, negative 1, 0. So now this is 2 by 3 matrix. So what did I do? I switched the columns with rows. And what's that called? Transpose of a matrix. Trace of a square matrix, remember you gotta have a square matrix, is basically the sum of the diagonal elements of a square matrix. So in this case, the diagonals are 3 and 2, so the answer is 3 plus 2, which is a number, not a matrix. So the trace is the sum of what? Diagonal elements. Vector form of a system of linear equation. So this is basically the vector form, correct? And A is the what? Matrix of coefficient, and this guy is what? Matrix of variables. This is matrix of what? Constant. So you can write that as AX equals B, and this is A, that's X, and that's B. All right. Algebra of matrices. In other words, how do you add, subtract, multiply matrices? Notice I didn't mention division because division is not defined in matrix land. So in order to add two matrices, they gotta have same dimensions. So all you have to do is what? Add the corresponding what? Elements and come up with the same dimension of a matrix you started with. Notice these are 2 by 3. So therefore addition is defined. In other words, they gotta have same dimension. Otherwise we cannot add. So in this case, the question was add. So first thing I do is check the dimensions, make sure they both have same dimensions. Once I make sure the dimensions are equal, then I add the corresponding elements, like 2 minus 1 gives you 1. Do you see it? Negative 1, what? Plus 0 gives you negative 1. 3 plus what? 5 gives you 8, and it goes. Similarly, you can subtract. So instead of adding each corresponding element, you can subtract each what? Element from its corresponding element from the next or previous matrix. What I'm saying is you're only allowed to what? Take the A11 from here. Let's say this is matrix A. Let's say this is matrix B. You're only allowed to subtract what? B11 from A11. In other words, you can't mismatch the subscripts. So you gotta keep the order the same. So in order to subtract together what? Let's say the answer is C, C11. Okay, that means the element in my addition of matrices A and B. Let's say the first position is C11. So what is C11 equal to? It has to be A11, what? Excuse me, this was subtraction. So it has to be A11, what? Minus B11. So in other words, you gotta go by the order. So that's basically what it is. However, when it comes to multiplication, it's a bit tricky. Multiplication is as follows. To find the product of two matrices, notice what's going to happen. The number of columns in the first matrix must match the number of rows in the second. In other words, if you were hoping to multiply A by B, check and see the number of columns of the first matrix in your product matches the number of, this is like the number of columns, matches the number of rows in the second matrix. So here, this guy is the number of columns of matrix A, has to match number of what? Rows, what? Of B. Otherwise, the multiplication will not be defined. However, once you made sure that you got the right dimensions, if you cancel these guys out, what's left, which is M and P, is the what? Dimension of the product. So this guy is my product. Division is not defined because not every matrix has inverse. Because remember, real numbers, you can divide real numbers. Let's say I divide what? 6 by 2, which is the same as 6 times 1/2, which is the reciprocal of what? 1/2. In matrices, not all the matrices have a reciprocal, which we call it inverse. Therefore, division is not defined. All right? So, with that said, let's see if we can multiply the following matrices. You got a 2 by 2 matrix for A. You got 2 by 3 matrix for B. You got row vector, which is 1 by 3. And then you got a matrix, which is 3 by 2. In order to multiply matrices, you got to remember from multivariable calculus, how did you go about taking the dot product of two vectors? Okay, the dot product of vector A and vector B was what? You take the first component, multiply that by the second, plus second component of the vector A times second component of vector B, plus so on and so forth. At the end, remember, we got a scalar. Same idea is true for multiplying two matrices. To begin with, make sure what? The number of columns in the first matrix matches the number of rows in the second matrix. Otherwise, the multiplication is not defined. In this case, these numbers match. So if I cancel these guys, what's left is 2, 3, which is the size of my product. So this is my product. Question, how did you get 5 and 13 and 9 and 8 and 16 and 12? Check this out. The way you do it, you take the row vector of the first matrix, dot product it with a column vector of the second matrix. In other words, to show you how I got 5, I took vector 1, 3, dot product it with 2, 1, which is 1 times 2, plus 3 times 1, which is 5. Do you see it? How did I get 8? Well, I took the second row and it's still dot producted with the first column. How? 2 times 2 plus 4 times 1. That's 8. That's how I got that. And so on and so forth. So to get these numbers, now you have to take what? The row vector of the matrix A and dot product it with second column of matrix B and so on and so forth. Do you see it? The next one is B times A. This is 2 by 3. This guy is 2 by 2. The number of columns here does not match the number of rows there, so this is not defined. Make sure you only find the answers for product of two matrices when it is defined. What about C dot or C times D? Well, just to make sure you know these are not dot products, let me just erase these dots. These are like multiplications, correct? They're not dot product. It's multiplication of matrices. Sorry about that. So what is this? This is 1 by 3. That's 3 by 3. Hey, these guys match. So therefore, the product is defined. And if you cancel these guys out, that will tell you what the dimension of your answer should be. So the dimension of my answer should be what? 1 by 2. Okay, so this will be a row vector. How do you do that? You take the row vector of matrix C, dotted with column what? Vector of matrix D as in David. So that would be -1, 0, -1. That gives you -2. Now you what? Dot this row vector with this column vector. 1, plus 2 minus 2 is 1. So there it is. This guy is what? 3 by 2. So, but A is what? 2 by 2. These guys match. Therefore, the answer is the product is defined. If you cancel these 2's, the product should have a dimension of 3 by 2. Notice we can tell ahead of time what would be the dimension of the product before we multiply. So the product has to be 3 by 2, and that's basically how I got this answer. You know how I got it, don't you? I took the dot product of the row in matrix D and dotted with what? Column vector in matrix A. So I'm taking the dot products. Okay, the last one is what? C times B. So this is 1 by 3, that's 2 by 3, but remember these guys don't match, so the multiplication is not defined. One of the takeaway from here is matrix multiplication is not commutative, meaning the order matters. In other words, you may get an answer when you multiply A by B, but the minute you switch these guys around, the dimensions might get messed up. Therefore, matrix multiplication is not commutative. Did we do any problem like that here? We sure did. There it is. A times B, we had an answer. But then B times A, it was undefined. Do you see it? So therefore, A times B is not necessarily B times A. Do you see it? All right. One more thing, take away from this ongoing story about matrix operations. If the product of two matrices happens to be 0, matrix, of course, that doesn't mean either A or B was 0 to begin with, like real numbers. That's not true. Case in point, let's take matrix A 3, negative 6, negative 1, 2. Matrix B 2, 6, 1, 3. Believe it or not, when you multiply these two matrices, you get the 0 matrix, which is 2 by 2. But neither of them was 0 to begin with. So that idea, if the product of two numbers is 0, one or both had to be to 0 to begin with, does not apply to matrices. Incidentally, when we say 0, we mean 0 matrix. Okay? So, system of linear equation basically looks like this. If these constants are not equal to 0, the system is called non-homogeneous. If these constants happens to be 0, B1 and B2 is 0, then the system is called homogeneous. And all these coefficients, A11, A12, A21, A22, including B1 and B2, they're constants. So this would be a system of equation in two variables, two equations, two variables, just like algebra classes. This guy has three equations, three variables. But remember, I can write it in vector notation, A times X equals B vector, correct? In this case, notice in the case of system of linear equation, the number of rows of your coefficient matrix represents what? The number of equations in your system. And the number of columns here, which happens to be n, represents the number of variables. So m is number of equations, n as in Nancy represents the number of variables. So in these foregoing questions, like last two examples, number 1 and 2, m as in Mary is equal to n as in Nancy, because I have two equations, two unknown, three equations, three unknowns. So this is the case where number of equations matches the number of variables. Do you see it? So if that's the case, what are the possible solutions? Okay. The possible solutions are as follows. Either you get a unique solution, which means one-of-a-kind solution, And in that case, the system is called consistent, or sometimes it's called independent, just like algebra classes. Or you may have no solution. In that case, the system is called inconsistent. All right. Or you may have infinite many solutions, and the system will be called dependent. So independent, inconsistent, dependent. So now let's go over additional operations. So in the next video, we get to solve some system of linear equations. Once again, if the product is 0, that doesn't mean either of the matrices was 0 to begin with. Case in point, there it is. More properties or rules of matrix multiplications. Excuse me. If the dimensions are appropriate and you multiply matrix A by the sum of matrices B and C, so you gotta follow the order. So this has to be AB plus AC. You can't switch them. On the other hand, if this is A times B times C, so the answer is ABC. Then again, order matters. If you take the transpose of a product of two matrices, the order gets to be reversed. So in this case, the answer is B transpose times A transpose. So make a note of it. The transpose of product is the reverse transpose of the original matrices. So this is not A transpose times B transpose. Notice the order got reversed. But when it comes to addition and subtraction for transpose, the order stays the same. In other words, you go A transpose plus or minus B transpose. However, in the case of multiplication, the order gets to be reversed. And that pretty much does it for this section. Thank you.